Potassium. Let's look at potassium as it relates to plants. Etymology. The name comes from the English word potash. Potash is the material that accumulates on the bottom of cooking pots when you cook over an open fire. As the wood burns, it releases material in the smoke, and some of this is potassium. It accumulates on the bottom of the cooking pot. You could scrape that off and use that as fertilizer. Also, ashes from the fire could be used. The chemical symbol K comes from kalium, which is the medieval Latin word for potash. Kalium may also be derived from the Arabic quali, which means alkali. Soil basics. The average potassium content in the Earth's crust is about 23 grams per kilogram, which is a rather large amount. The largest part of this is bound in primary minerals and in the secondary clay minerals, which largely make up the clay fraction of the soil. Clay content of the soil is to some extent dependent on the soil parent material, but it is also affected by pedogenesis, which is the formation of soil from rock. Old, highly weathered soils are often low in potassium. The main source of potassium for plants growing under natural conditions comes from the weathering of potassium-bearing minerals. The potassium content of the soil is also dependent on the type of clay minerals present. Organic soils are frequently low in clay and therefore in potassium as well. This table gives you the potassium concentration of some primary and secondary clay minerals. If we have things like alkali feldspar, you're looking at a concentration of 32 to 120 grams per kilogram. Calcium-sodium feldspars, on the other hand, are very low. Muscovite, which is a potassium mica, a sedimentary type material, is between 60 and 90, whereas biotite, which is a magnesium type mica, is going to be lower. Vermiculite, which is a type of expanded mica, is lower as well. Montmorillonite, which is a type of clay, has a low content. It really varies on the type of primary and secondary clay minerals. Heavily weathered clay soils with potassium depleted minerals may actually affix applied potassium and additionally reduce availability. Potassium is attracted to ions because it is a monovalent cation and can easily be picked up. When it is bound, it can be held quite tightly. The degree to which potassium fixation occurs is dependent on a number of factors, which include the charge density of the material, the extent of the wedge zone, that is the relative position based on the size of the atoms, the moisture content, the concentration of potassium, and the nature and concentration of competing cation species. Potassium is high on the pecking scale, but it's really going to depend on what else is there, because there are some cations that are more attracted to clay minerals. Soil clay concentration is not only of importance for potassium release and fixation, it also considerably influences the mobility of potassium in the soil. Soil potassium can be divided into three fractions: the structural element of soil minerals, including interlayer potassium, the potassium adsorbed in the exchange form to soil colloids such as clay minerals and organic matter, the potassium that is present in the soil solution. Remember, you may have potassium in the soil, and it may be in the soil solution rather than attached to something else. We consider that to be readily available potassium. That doesn't mean that it's necessarily going to stay put. By far, the greatest fraction of soil potassium is located in the mineral structure. Exchangeable potassium represents only about 5% of the total soil potassium, which is good because if you get too much exchangeable potassium, it displaces other elements from the CEC and affects the availability of other elements that are needed. Potassium released by minerals into the soil solution can be taken up directly by plant roots or adsorbed by soil colloids. 1 micromole of potassium is approximately 39 milligrams potassium. Therefore, 1.7 micromoles is about 67 milligrams per kilogram, or 67 ppm. The total level of 41.5 micromoles is about 1.6 grams per kilogram, or 1600 ppm. The exchangeable part is normally lower than the non-exchangeable part. The mineral potassium is normally quite high compared to the other two. You get an equilibrium set up between the adsorbed potassium and the free potassium in the soil solution. As potassium is taken out of the soil solution by plants, you will have more being released into the soil solution off the cation exchange capacity. This acts as a buffering for potassium in mineral soils where you don't want all in the solution because then it could be easily leached. In organic soils and sandy soils, without the ability to absorb potassium, little buffering occurs and potassium concentration can change quickly depending on plant uptake, fertility, fertilizer application, and leaching. Potassium uptake. Potassium buffering power largely controls the potassium diffusion rate towards the plant roots and therefore the uptake of the crop. Potassium is needed in higher amounts in plants and therefore is easily picked up out of the soil. Crop pickup material out of solution. You've got the buffering power, which is going to allow more into solution. Potassium is probably the most important cation found in the plant next to hydrogen. Again, potassium is used for ion exchange and ion regulation. It is easily taken up and translocated through the plant in the cationic form. Accumulation by the roots is achieved by plasma membrane transporters, which are able to adjust quickly to a wide range of potassium in the soil solution. Potassium is extremely important for plant ion regulation. The transporters are thought to be specific selective channel transporters located in the plasmalemma and the tonoplast. There are both outward and inward facing channels which respond to the electropotential gradient. That means potassium is pumped from one side of the membrane to the other or back in different channels rather in the same one. It doesn't just occur by diffusion, but is actually a transport that is regulated by the plant to make sure that the concentration on both sides of the membrane are exactly what the cell requires. Translocation in plants. Potassium is highly mobile in plants, and long-distance transport takes place in the xylem and in the phloem. The concentration in the exudation sap of decapitated plants ranges anywhere from 10 to 30 moles per cubic meter. Of all organic species present in the xylem, potassium generally has the highest concentration. The phloem sap concentration is in the range of 50 to 150 moles per cubic meter. Transport of potassium in the xylem is exclusively from the root to the shoot, whereas in the phloem it may be directed towards the various sink organs, both in the shoot and including storage roots and tubers. Transport of potassium therefore comes out of the roots, goes up to the upper part of the plant where it is used. Once it is put into the phloem, it can either go into the sink organs, which include the apical meristem, which includes the developing leaves, or the floral meristem, which includes the developing seeds and fruits, or it can be pulled out and sent down to the storage areas in the roots or tubers. Potassium is therefore extremely important in plants.